Good afternoon, everyone. Today is the fourth day of our course that is on geospatial driven modeling for urban hazard and risk analysis. Now, today the topic of discussion is geospatial driven research and modeling for heat waves and urban microclimate studies. Now, as we are aware that urban areas, they show a distinct climate. They sometimes experience, urban areas mostly experience higher temperature than their surrounding areas, and they have other like weather parameters are also different. So let us start with our deliberation on urban and how this remote sensing and GIS technology can help in modeling and research in urban microclimate and heat wave analysis. So if we look at urban climate, urban microclimate is affected by four major parameters. One is your height of roughness feature, like how is the building is low rise, mid rise, high rise, or it is dependent upon your even it applicable to vegetation also, whether it is soil, grasses, bush or trees, and it is dependent upon your packing of roughness features also, like what is the density of your roughness features. So here building and vegetation, they behave as a roughness features, and it is also dependent on what is your surface cover, whether it is impervious surface or pervious surface. Impervious surface is also if it is low plants, it is plants or it is soils. So it is dependent upon your these surface cover fractions also. And then thermal admittance of materials, like whether it is heavy material or lightweight material. So and it is dependent upon your metabolism. So if we look at in this area, like where the remote sensing can help us, so if we look at urban structure, like urban structure is your permeability. What is the surface cover fractions? Now here we define surface cover fraction as three aspects: building surface fraction, impervious surface fraction and pervious surface fraction. See here, impervious from climatic point of view, impervious surface fraction includes your road and paved area. It doesn't include your buildings. Buildings are included in your building surface fraction. So here we have a host of 2D remote sensing data, like number of remote sensing data sets are there where you can classify your and with varied resolutions where you can classify your pervious and impervious surfaces. Now second aspect of your urban second aspect is urban form or 3D geometry of urban form. It is defined by urban canopy parameters such as building height, sky view factor, height width ratio, etc. So for this we require 3D information. We require information on building footprint as well as we require information on building height. So here also lot of data sets are available, like LIDAR is there, INSAR is there, aerial photographs or VHRS optical stereo. Now if you look at urban fabric, they are also basically mostly it is made of concrete or asphalt. But if we want to look at the tiled structures or we want to differentiate between asphalt, road and concrete, then we need hyperspectral data. Now fourth aspect of your urban climate, like whether the impact is there, that is urban metabolism or the anthropogenic heat or whatever the surface urban energy flux is. So their thermal remote sensing can help us. So now we'll discuss one by one the each aspect of our urban microclimate. So if we look at the pervious surface fraction, impervious surface fraction, so here you can see like building surface fraction is area of the building and divided by the total grid area, total area. Pervious is the area of the pervious area and divided by total area, and impervious surface includes your road, paved surfaces, bare rock area, that all comes into under your impervious surface fraction. So we know that all these surface fractions we can easily compute using your remote sensing data, and here I can show you some of the results, like where urban surface cover, like pervious surface fraction, when it was correlated with your land surface temperature obtained from thermal remote sensing data, you can see that pervious surface fraction shows negative, very strong negative correlation with land surface temperature. Means as your pervious surface increases, your temperature comes down. Similarly, if we look at the land use land cover part, so we can see that water shows the least temperature and bare soil and built up shows the highest temperature in broad land use land cover classes. Here we can see one this building surface fraction also. So this building surface fraction is showing that as your building surface fraction increases, especially in summer monsoon, your temperature increases. But however, in winter it shows a bit of your non-linear relationship, and that is mainly because of your shading, and sometimes your LST is that pass of the satellite which is used for your LST, it is morning times like 10:30 am or 10:45 to 11 am, which is at that time your building surfaces are not so much heated up. Similarly, if you look at the pervious surface fraction, it also shows that in all the seasons, as your pervious surface fraction increases, your surface urban heat island intensity decreases. Now we come to the second part of your urban geometry. So we have known that urban canopy parameters, they define your 3D urban geometry, and there are different parameters like mean building height, standard deviation of building height, area weighted mean building height, building surface area to plan area ratio, frontal area index. We'll discuss all these parameters. Like there are number of parameters which are used for defining your urban canopy parameters. And these urban canopy parameters, they form an important input into urban canopy models for your weather forecast, for your climate studies. And but however, there is a very less information available related to urban canopy parameter. So this urban canopy parameter can be generated using 3D GIS database, because we use morphometric equations to compute all these parameters, and input data is basically your building footprint and building height. So this 3D GIS database contains your building footprint and building height, and this we can utilize for computing your different urban canopy parameters. Now if we look at aerial photography, so it is limited availability. Similarly, airborne LiDAR or INSAR, they have the limited coverage, and sometimes the data is costly. So there is that, because of that, in developing countries especially, there is non-existent of these kind of urban canopy parameter or 3D GIS database. So in this study, we have developed an methodology to retrieve these parameter using very high resolution optical stereo, which is comparatively has lower cost and has wider availability. And it has numerous application in urban climate research, like you can study your ventilation potential, your local climatic zonation, urban climatic map, and then inputs through urban climate models, and so many other further applications. So this is a graphical representation of urban canopy parameter. We had already discussed about surface covers like building surface fraction, pervious surface fraction, and impervious surface fraction. Now there is one canopy parameter is complete aspect ratio. It is basically total area of ground plus total area of wall and total area of the building surfaces, and divided by the grid area. Similarly, if you look at the building surface area to plan area ratio, here you don't include your ground area, but otherwise it is similar to your car. Mean building height, when you take the mean height of the buildings in the particular grid area, and there is a sky view factor. All these parameters, they have impact on your energy exchange, they have impact on your how buildings, like how this roughness surfaces interacts with the atmosphere. They have impact on UHI and temperature profiles, even the wind profiles. So all these are affected by these urban canopy parameters. Similarly, like if you look at this sky view factor is the hemispherical sky, which is open when you are standing in a urban canyon, like this is an observation point. So how much hemispherical sky is visible. It also has an impact on your wind flow as well as your urban heat island formation. Now if we look at one more parameter, that is frontal area index, which is one of the major parameter which has impact on your wind flow. So it is basically the obstructing the wind flow. And now height width ratio is basically height, average height divided by width of the street. Then your frontal area density, where you compute frontal area index at different heights. Your plan area density, where you compute your plan area of like building surface fraction at different heights. Similarly, roof area density. So all these parameters, they have a lot of impact on your trapping of the heat and your dissipation of heat from the urban fabric. Now in this methodology, we have taken very high resolution optical satellite stereo, which is sub-meter resolution, 0.5 meter resolution. And with that, we have taken multispectral data also. After photogrammetric processing, digital surface model and digital terrain model was generated, and ortho images are also generated. So this digital surface model, digital terrain model, when we use the equation of NDSM is equals to DSM minus DTM, here you need to understand one concept, that is digital surface model. Digital surface model is the surface model of an urban area, and that includes your height of your above ground objects like building, vegetation and other this one. And digital terrain model is when you remove your above ground objects from your terrain, this surface model, then it is basically the terrain model of your terrain, that is digital terrain model. So when you subtract digital terrain model from digital surface model, you get a normalized digital surface model, that is NDSM, and this NDSM contains height of your buildings, vegetation and all above ground objects. Now to get your building heights only, you have to filter the pixels with vegetation, you have to filter the pixels with elevated road, rail and metro network, and there is pixels more than 2 meter in height was taken, and less than 2 meter in height was considered as null value to get the building surface area and building height. Now using land use land cover, this graded surface cover fractions were calculated, like building impervious and impervious surface fraction. And when we get this building height, then mean building height and standard deviation of building height, and all aspect ratio like complete aspect ratio, BSAPR, height width ratio, building volume, using your this one morphometric equation. So details of this work is you can see in this published paper in more detail, where every parameter and equation is described. This is a publication which has been in IIRS, so you can refer this paper for your detailed of this work. But here you can see the digital surface model and subsequent digital terrain model of the area of Delhi and its surrounding region. This is your normalized digital surface model and land use land cover. Using normalized digital surface model, mean building height and standard deviation of building height was calculated, and even the building volume. So these three parameters are calculated using characteristic equations like height, mean building height and deviation. That is very simple, but building volume requires your total wall area. So after calculating this total wall area, building volume was calculated. Now this digital terrain model which was generated, it was validated with respect to DGPS observation which we collected from the ground, and we have found that it has error of RMSE error of 1.33 meter and 1.78 meter and 0.3 meter. So it is showing very good performance with respect to your DGPS observation on the ground. And when this building heights when we computed the building height layer, there were ground measurements were collected from the ground, like distributed ground points, using Leica distometer. There is a laser distance meter instrument that is works on the principle of laser, and here we can measure the building height from the ground. So that building height was measured and then it was validated. So here you can see that most all the height groups are showing RMSE of 1 meter. So because of that is what this data is found to be quite suitable for going for further analysis of your computation of urban canopy parameter. So here you can see using DSM, we can compute this sky view factor also, which is a key parameter to affect the building geometry. and it has impact on ambient temperature and UHI. So here this is using DSM, digital surface model. This sky view factor has also been computed. So here you can, and these were this sky view factor has been validated against ground observation. Like you can see, like this fisheye photographs were collected from the ground, and from this the hemispherical sky, this gap fraction was computed, and this gap fraction was validated with your layer, this layer, and we have found the mean error of 0.019 and CRE of 8.13% and RMSE is 0.046. So this is also showing very good accuracy with respect to your ground measurement. And here if we look at the sky view factor of the total area, we can see the maximum sky view factor is within this range 0.4 to 0.9. But if we look at the building SVF, like within the building area, then we can see built up area, we can see that it is ranging from 0.4 to 0.65. Maximum values are falling in this range. Now if we look at sky view factor versus land surface temperature, so we can see that nearly around 0.4, that as your sky view factor is increasing, the temperature is going down, but beyond a point it starts again increasing. So this is shows the impact of sky view factor. And if we look at the building height with LST and surface heat island intensity, so we can see that buildings are showing a non-linear relationship with the LST, because building height is a 3D parameter. So LST is mostly the temperature of your land surface. So it is basically oversampled your 2D surfaces rather than your 3D surfaces. So that's why building height shows very less correlation value with LST, and it shows a non-linear relationship. Similarly, here you can see that height width ratio of Delhi and its surrounding region, and here you can see that most of the area is falling between your 1 to 2 to 3, like up to 4 5 height width ratio, and very less percentage is falling beyond that. And if we look at complete aspect ratio, then also it is, we can see that most of the values are falling within the range of your 0 to 2.5 value. And similarly we can see the surface roughness. This is also one of the very important parameter for understanding your flow of the wind in urban area, like because whatever if the surface roughness is more, it has an impact on your wind flow. So in this area what we have done, we have used this surface roughness, and we can even calculate your ventilation potential, that we'll discuss in further slides. So here this has been classified into 3 classes, like if it is less than 0.5, it is ventilated, and if it is 0.5 to 1, then it is partially ventilation, and if it is more than 1, then it is weak ventilation. Similarly, if we look at zero plane displacement height, it has also, like there is one formula which has been used to compute this zero plane displacement height, and which is dependent upon volumetric averaged height and your building surface fraction. So here we also, it can be classified as, if it is less than 3, then it is ventilated, and if it is more than 3, weak ventilation. This classification has been done based on the guidelines given by Metzarakis and Mayer. So further, after this optical satellite stereo, we have even utilized UAV data, unmanned aerial vehicle data, for computation of these urban canopy parameters. For that, the free data, open source data available from IIT Roorkee for Khanjarpur Roorkee and Chingrajpura Bilaspur, it has been used, and where we have calculated your that orthomosaic, DSM, DTM and field data were used to carry out this study. Here you can see the 3D model of your one of the area of like Khanjarpur Roorkee, and here you can see the building footprint. These building footprint has been measured against your digitized building footprint from ortho, and we have found a very good accuracy, like 81.6 of completeness and 90.9 is correctness, 19.9% is correctness. Similarly, building height were also like validated against ground observation, and here we have found the RMSE of 0.05 meter, like nearly 5 centimeter error, which we have found in the automatic height extraction from UAV data. Now this UAV data has been utilized using morphometric equations for computing number of parameters like average building height, volumetric average building height, wall to plan area ratio, mean building height, zero plane displacement height, complete aspect ratio, building surface area. So there are so many parameters which has been computed, and they have been validated against, like here we have in one aspect we have extracted building footprint from using OBIA method, object based image analysis methods, and we digitize the building footprint also, and then we computed all the canopy parameters using digitized building footprint as well as classified building footprints. So here we can see that it has very good correlation in most of the parameters. It is showing very high correlation in both the data sets. So it shows very low RMSE value and strong correlation with data collected from ground, and all UCP shows high correlation coefficient and low AD values with digitized footprint. So this is some of the parameters they performed quite good, and we have found that this UAV data is very good for computation of your urban canopy parameters. Now these parameters were shared with the National Center for Medium Range Weather Forecasting, NCMRWF, and IMD for ingesting into your high resolution urban climate model. So when we have ingestion of these urban morphology data, we have found significant improvement in weather parameters. Like you can see, like this is Mauritius, India is the experiment which includes your morphology data, whereas these experiment doesn't include your best 20 doesn't include your urban morphology data. And Mauritius London includes your morphology data based on your London data sets, like the equations developed based on London data sets. So we have found that equations, that like empirical relationship which was developed using Indian data set like urban morphology data of Delhi has performed the best, and even wind speed has also improved after ingestion of Delhi morphology data, almost 25 to 29% improvement. So this the detail of this work is also can be further detail can be accessed at this can be studied on this publication. Now we come to the third aspect, that is urban fabric. So urban fabric like composition of materials. So here most of the data which is available, that is your airborne data. Like if we talk about Hyperion or Prisma, which is 30 meter spatial resolution, it is an inadequate resolution for studying your composition of materials in urban area. We need data of almost 1 meter or 2 meter resolution, but since airborne data is limited availability, so this aspect is still in research domain, but definitely with the availability of hyperspectral data, this composition of material albedo can also be studied in detail. Now fourth aspect is your urban activities or urban metabolism, that is anthropogenic heat flux. So we are aware that for natural land surface, your surface energy balance can be described as a summation of your latent heat flux, ground heat flux, and sensible heat flux, and that summation is equivalent to your net radiation. But for urban surface energy balance, your one component, your anthropogenic heat discharge, is also to your heat flux component. So based on this urban surface energy balance equation, we can compute urban metabolism using your thermal remote sensing data. Here you can see that this is based on some set of equations which has been derived over a period of time using thermal remote sensing data. From literature, we can compute this one. This is net radiation, your ground heat flux, then your latent heat flux, and then sensible heat flux. So based on this, then we can compute your even anthropogenic heat flux based on solving your, it is a anthropogenic heat flux is a residual energy flux after summation of your latent heat flux and latent heat flux, ground heat flux, and sensible heat flux, and then this subtracting it from the net radiation. Now, this is part of like our different aspect of your urban microclimate parameters. How remote sensing can help you out to get the information about those parameters. Now we'll come to the very most talked about phenomena, that is urban heat island. Whenever we talk about urban microclimate or urban climate, this phenomena is the most talked about phenomena, where it is basically urban surface is hotter than that of surrounding non-urban regions. So here you can see that most of the urban area they exhibit, but since this urban heat island is not a phenomena which is very consistent phenomena, it is a very dynamic phenomena. You will find that sometimes in night time your intensities are different, heat island intensities. Daytime it is dependent upon your diurnal variation, as well as your, it has diurnal, seasonal and annual variations. And here if we look at this daytime and nighttime, in this study they have found that surface temperature has quite a good difference in during daytime between air temperature and surface temperature, but nighttime your surface temperature and air temperature is almost follow the similar kind of profile. If we look at this urban heat island, so what contributes to the urban heat island? So where there we understand that albedo of urban materials, like because most of the urban materials are low albedo materials, so they low albedo materials, so they have lot of absorption of the heat. There is a reduced vegetation in urban area, and there is a anthropogenic heat. Urban geometry also plays a role in trapping of the heat. And then weather and geography, like synoptic weather conditions and geography, that like location of your urban area, they all has an impact on UHI formation. So there is heat absorbed by building, heat from traffic congestion, so all these use of air conditioner, so that all adds to your increased heat in urban area. Now, as a like sometimes we can some person may argue that we can, if the heat is more, then we can use some mechanical means to keep our thermal comfort. But there is like there are some very serious side effects of your urban heat islands. Like first comes your increased energy consumption. As your temperature increases, your energy consumption also increases in urban area to keep the heat low, or to keep the cooling load increases. And there is increased risk of heat related mortality and morbidity. Like when the temperature is high, there is chances of heat cramps, heat stroke, they also increases. Even it has impact on air pollutants and greenhouse gases. Like it is established that as your temperature increases, there is a increase in the ground level ozone, and that ground level ozone is very allergenic constituent of your urban atmosphere, and it increases your respiratory problems. So this also has an impact on your air pollutants and respiratory issues in urban area. Even increasing UHI has an impact on your water quality, because your water temperature also increases, and it changes your sometimes the pH and the quality of your water, and that has impact on your urban area as well as your the aquatic life. Now, if we look at urban heat island, see most of the time we use urban heat island as a single term, but urban heat island is basically of different type of urban heat island are observed this over a period of time. Like you can see there is one surface urban heat island. Surface urban heat island is the heat island because of your surface temperature, and it is studied at local and micro scale. And if we use the direct measurement, we need to attach the temperature surface sensors to the surface. But this type of urban heat island is mostly studied using your remote sensing data, where you have thermal remote sensing, satellites data, aerial or UV data, basically using your land surface temperature. Now, second is your canopy layer urban heat island. So, urban canopy is the area between your ground to the highest roughness element, that is your urban canopy. So basically the area between your buildings that comes under your canopy layer urban heat island. So this can also be studied using your temperature sensors at fixed station. That is the maximum of your urban heat island is studied in the initial phase of your urban climate research has been done using your temperature sensors installed at different location. Like you might have studied that might be aware that the urban heat island is mainly studied by taking the temperature difference between urban station and the rural station. And there are mobile towers is one of the common method to use study this urban canopy layer heat island. Now sometimes using mini SODAR or mini LIDAR, these can be studied, and sometimes you can use it your modeling can also be utilized to study this canopy layer urban heat island. Now third one is your urban boundary layer heat island, where it is whatever boundary layer, urban boundary layer is the height till your effect of urban surfaces go. So this urban boundary layer heat island is also studied using your temperature sensors mounted on aircraft, balloons or tall towers. And it is sometimes it is used study using a SODAR, LIDAR or profilers. And there is one more which is less studied aspect of your heat island is subsurface heat island, and that can be studied using temperature sensors within the substrate or your ground. So if we talk about in mostly remote sensing, we mostly talk about your surface urban heat island, because that is what our satellite and sensors we use to estimate the land surface temperature, and that can be utilized for your surface urban heat island in the city. So there are a number of satellites, but mostly used your Landsat series data and MODIS data. So MODIS provides you 4 pass daily, and it has a resolution of 1 kilometer, whereas Landsat provides you data in every 16 to 24 days, and it has a resolution of, although it collects the data at 100 meter, but data is provided at 30 meter after processing. And there is Ecostas data is also there, and some other data sets, but most of the data sets are coarse resolution data. At Landsat and MODIS is the maximum utilized data set for studying your surface urban heat studies. Now in this study we can see that there are different algorithms to retrieve LST from your remote sensing data, thermal remote sensing data. Like you can use single channel algorithm or mono window algorithm or split window algorithm depending upon your data. So here I am presenting one example of using single channel method on Landsat 5 TM data of October 2008 for Chandigarh region. So here also you go step by step and solving different equations, and then you will generate your land surface temperature data. Similarly, this is using Landsat 8 October 2015, a split window method has been used, and this land surface temperature generated. So you can see that land surface 37.73. So one thing which you can observe in this reason that in both the data sets, your higher temperature is also increasing and lower temperature is going a little bit down. So your range of temperature is increasing. Now using this land surface temperature data, we can utilize it to study your different season and seasonal aspect of your that UHI formation or land surface temperature variation. So here we have used 4 seasons like May, October, August and February. So this temperature, the Landsat data was taken, and we could study that how this variation is coming in different seasons in temperature, range of temperature as well as minimum and maximum temperature. And so once we study this surface urban heat island intensities, see here surface urban heat island intensity is computed based on the difference between urban and rural temperature. Now urban here it is defined as a temperature of your dense built up area. Temperature is defined as the urban temperature, and temperature of agricultural area is defined as the rural temperature. So here you can see, with I have already shown you this building surface fraction. Here you can see that building surface fraction and impervious surface fraction, they show a positive, positive correlation with the surface urban heat island intensity in most of the seasons, where you can see that as your fraction increases, your temperature also increases. However, in winter it has shown a little bit of non-linear relationship. Pervious surface fraction shows negative strong correlation with your surface urban heat island intensity. As your this pervious surface fraction increases, your temperature also reduces. Building height, as I have already shown, that it shows a non-linear relationship with your surface urban heat island. Now, if we look at your this land surface or surface urban heat island studies using your thermal remote sensing data. So there are few issues with the thermal remote sensing data for studying your urban heat island. The first is your data acquisition time. That there are so many researchers, they have reported that most of the time your land surface temperature, that pass time, like Landsat data, like generally it has a pass around 10:30 to 11. So this 10:30 to 11 is generally do not coincide with your maximum urban heat island. So generally your heat island, maximum urban heat island is shown generally at night time in arid regions, and sometimes it is in the afternoon time, but it generally do not coincide with maximum UHI. And if you talk about diurnal profile, that is also difficult to get because widely used data is Landsat. So there is that provides you mostly the daytime pass. Cloud cover, fog, and there are some other issues. They create a data gap, so that decreases your data utility also. And there is a issue of getting the high spectral, spatial, and temporal resolution with same instrument. For example, Landsat has very high spatial resolution as compared to other sensors, but it doesn't have very good temporal resolution. While MODIS has very good temporal resolution, like it is giving 4 pass every day, but it is difficult, it is giving the data at 1 kilometer resolution, spatial resolution. So all these issues we can address using your computational modeling, or using your in this study we have used integrated WRF model simulation for studying the UHI of in this area, in Delhi urban area. So here Delhi urban area was taken, and for this 2 domains were created for studying this urban heat island studies. One is 0.5 kilometer domain and one is 1.5 kilometer domain. 1.5 kilometer domain was created to taking into account your regional phenomena, regional weather conditions into account. Now, resource set to LIS4 has been utilized for creating 3-class urban LULC. See, in WRF, we can depict urban area as a single urban class, single built-up class. So, in single built-up class, it gives the single value to the whole urban area. It is considered as a increased roughness with the increased roughness and volumetric capacity. So this, but in 3-class, but urban areas are quite heterogeneous. So to address that heterogeneity, 3-class urban LULC was generated using resource set to LIS4 data. And even land surface parameters such as your leaf area index, vegetation cover, and vegetation fraction, and your elevation, that also been updated in the model. And NCEP GFS data of 0.25 degree was considered as initial and used for initial and boundary conditions. Now all this has been integrated into WRF model, and downscaling of meteorological parameters was done at 0.5 kilometer. So we can see when this further it has been validated with ground observation and MODIS LS3. Now to address the seasonal phenomena, 3 seasons has been simulated, like summer, monsoon and winter, and 3 days simulations were carried out to because of it requires a lot of computational resources. So for that we carried out only for 3 days in a season. Now here this is we have developed a methodology to generate this 3-class urban land use land cover using resource set list 4 image, where in the first step the image has been classified into broad classes, and later on it has been converted into high intensity residential, low intensity residential based on the percentage of built up in a particular grid cell size. And then industrial, commercial and transport layer, which is the third class, was digitized and was given the different codes as per USGS classification. So here you can see the details of your 3 class urban area. This is a low density residential area, and here you can see that 3 classes are there: industrial, commercial, transportation, high intensity residential and low intensity residential. In this study, 4 simulations were carried out. In the simulation 1, we use the WRF model as it is, like all the land use land cover, like urban single urban built up class and land surface parameters, all were kept as default data set. In simulation 2, only this LULC was updated with 3 urban class urban LULC, and in simulation 3, LULC was kept as the default, but land surface parameter were updated to the simulation dates, and simulation 4, all the LULC as well as land surface parameter were updated. So we can see that when we update 3-class urban LULC and when we are going for high resolution urban high resolution weather modeling, if we update LSPs, it provides the best results. So it is the best of highest least error is found in when we update LULC and LSP both. So even when we evaluated the model performance with the IMD value, we have found that it provides a improved performance with high correlation and less RMSE values. And its performance evaluation of model performance models also shows that most of the pixels, like nearly 85% pixels, are falling within -1 to +1 degree difference range. So that shows that that model evaluation has quite good accuracy. And here also we can see that UHI formation in Delhi has been seen mostly during night hours. So here you can see that summer season data, monsoon season data and your winter season data. So night times your UHI formation is clearly seen. Now when we had studied the diurnal profile of surface urban heat island intensities, like in summer season we can see that during morning time 11:30 to 2:30 it has displayed negative heat island intensity, and that is basically because of your urban materials are low albedo materials and they absorb heat during this time. However, bare soil area or fallow land area which is in the surrounding, is that this phenomena is mostly seen in our arid and semi-arid region, that heats up faster than urban area. So your surrounding area temperature is more than your urban area, and that's why you can see the negative heat island intensities in urban area. Similar pattern is observed for canopy layer heat island intensities also, means temperature at 2 meter, where we have seen that it is showing the less heat island intensity, less value of heat island intensity during morning hours, especially morning hours. In winter season also the similar phenomena was observed, like from morning to morning times, especially at the time of satellite pass, that is near to 11 o'clock. It is showing the negative heat island intensities, and it's mainly because of your 3D geometry of urban area which creates shading. So because of that, urban fabric gains heat, keep on gaining the heat, take time to gain the heat, and it gains heat slowly as compared to your surrounding rural areas and heats up later, and most of the time night time it is showing a very good urban heat island intensities. So when we look at this lower urban heat island intensity and canopy layer heat island intensities, during nearly 11:30, it raises concern for use of thermal remote sensing satellite, which is generally past time around to 10:30 to 11:30 a.m. and for SHA studies, especially in arid semi-arid regions, which is surrounded by your agriculture cropland, sand or bare soil. So there we can see that it is like more, it is required to be studied more and more on this aspect. Now we come to the local climatic zonation classification. Now this local climatic zonation classification has been given by Stewart and OK in year 2012. So they have divided the urban area into 10 urban built up classes. Basically it is a classification system, it is a climate oriented classification system, and it divides the urban area based on urban form and function. So it divides the urban area into 10 classes like a compact high rise, compact mid rise, compact low rise, open high rise, open mid rise and open low rise, lightweight low rise, large low rise, sparsely built and heavy industry. So you can go through this reference which has been given here to see the details of these land classes, urban land use classes. And here this classification system divides the land cover also in 7 broad classes like dense trees, scattered trees, bush and scrub, low plants. Basically it covers your agriculture, urban park and grassland, and then bare rock or paved area, bare soil or sand, and then water. So these are the classes that is defined in this local climatic zonation. Now for local climatic zone preparation, there is one site that is known as BUDAPT site. So this gives you a methodology where you can select your region of interest, and it provides you the tool also. You have to digitize your training set for each local climatic zone class in Google Earth, and you have to upload your training samples in your that tool, and it will provide you the local climatic zonation map. So here you can see the local climatic zone map of Chandigarh, where overall accuracy is 85.3%, and you can see the accuracy of. So here one thing which we have found, that overall accuracy, although it's very good, mainly because of your accuracy of your land cover area, but urban classes has relatively lower accuracies. This is local climatic zonation map for your 2015 year, and now these maps can be utilized to study your changes in areas from 2008 to 2015. And here you can see that there is a change in area of like compact high rise and compact low rise area and open mid rise area. It has increased, whereas your open low rise has decreased, and even your low plant area has also decreased, and there is a increase in heavy industry also. When we analyze this local climatic zonation map with the land surface temperature data, so we can see that compact high rise and heavy industry, like here you can see the compact high rise and heavy industry, it is showing the highest temperature. Here you can see that compact high rise and heavy industry, it is showing the highest temperature, whereas water is showing the lowest temperature. Similar phenomena is seen in October 2015 also, like compact high rise is showing the highest temperature, and heavy industry and compact high rise are showing the highest temperature. So if we compare the land surface temperature of 2008 and 2015, we can see that overall there is an average temperature increase by 2 degrees centigrade from 2008 to 2015. But your pattern of like highest temperature is shown by the heavy industry, whereas second highest is shown by the compact high rise. That remains same. This is also bias from mean. It also shows that increase in heavy industry and compact high rise, whereas it shows less temperature in dense trees and water. Now we had discussed about your about the temperature aspect, which is the most studied phenomena you can say, and we understand that urban heat island is basically the elevated temperature of urban area. But there is one more phenomena, like mean wind speed is mostly lower in urban area. Like because tall buildings, they form barriers and they create rugged relief which will lead to turbulence. Although it has been observed that if we have the adequate ventilation in urban area, it can assist in mitigating UHI effect. Now different type of like packing and height of roughness element, they create different kind of flow, like isolated roughness flow, wake interference flow, or skimming flow in urban area. Here you can see how these roughness elements create first a barrier, and in the backside of the building it create a turbulent zone. Now to study this ventilation or wind flow aspect, we can utilize the 3D building database. Like I have already told you that there are urban canopy parameters, and few of the urban canopy parameters can be utilized for studying your urban ventilation potential. So here the building height was taken from the stereo data set, whereas building footprint were digitized using your ortho images, and building height were measured in photogrammetric software, in 3D domain with the 3D mouse and 3D glasses. So we have found like there is building polygons. The important aspect of your 3D building database is your building polygons, which you can either digitize. Building polygons means building footprints which you can digitize, or either you can use segmentation based method like OBIA based method, object based classification method. And in new like with the new techniques which are coming up, you can use even deep learning models for identification of building footprint. Now if you look at height measurement, either you can measure it using 3D environment, or you can automatically extract using your high resolution optical stereo, either optical stereo of very high resolution like sub-meter resolution, or UAV data, or you can utilize even your LIDAR or INSAR or some other data sets. Now for validation of height, as I have told you earlier, that field measurement and Leica distometer has been utilized, and we have done the validation of height from using this ground control points, ground observed data, and we have found very good accuracy of measured height. To compute some of the complex urban canopy parameters like frontal area index, sky view factor, and height width ratio, there is one tool has been developed at IIRS, that is known as Urban Morphology Extractor, where the input data is 3D building database. And this also, you can see the detail of this tool also in this published research. So here you can see this the building height distribution over 50 meter by 50 meter grid in this area, like low rise, medium rise, high rise, and skyscraper. And then you can see that computation of roughness length, and like this is zero frontal area distribution. Using these parameters, we combined and we have calculated surface roughness and zero plane displacement height, which I had already explained in the previous slide, earlier slide, that we can calculate using some morphometric equation, and based on this criteria which is given by Metzerakis and Mayer, these layers has been combined together, and we have classified the map into ventilated, partially ventilated, and weak ventilation area. This there are temperature, wind speed measurement were taken in campaign mode, and we have found that ventilation path map shows high lower temperature and higher wind speed in ventilated area. Here you can see that ventilated area shows the lower temperature comparatively and high wind speed as compared to the weak ventilation area. There you can see the temperature versus ventilation class and wind speed versus ventilation class. So now this we have discussed different aspect of remote sensing data and GIS technology, geospatial technology, where it can be utilized for your studying the urban microclimate. Now there is one more aspect of your urban area where we talk about heat waves. So heat waves, we have seen over a period of time that frequency and intensity of heat wave is increasing in last few decades. and it leads to very uncomfortable situation, health hazards. It is responsible for heat related mortality, morbidity, and it has a lot of impact on economy also. And this has also been observed that urban area, they are more vulnerable to heat waves because they have pre-existing UHI phenomena, and they will provide positive feedback to your heat wave. So we have to understand the impact of urbanization on heat wave. So here you can see that overall globally your heat wave frequency and this one in intensity frequency is increasing. So for studying this, the MODIS LST data available on Google Earth Engine has been utilized, and study period was considered as April, May and June because this is the most heat wave period. So there are some code has been written in Python to extract the daily temperature on each grid, and 7 heat wave indicators were computed. These heat wave indicators were identified with respect to their compatibility with this LST data. So there is average heat wave duration, maximum heat wave duration, cumulative heat wave days, maximum heat wave events, maximum warm days, maximum heat wave temperature, and maximum warm days temperature. They have been combined using your AHP, analytical hierarchy process, and based on that there is one layer was created, and to do the hotspot analysis, LULC and population layer from GHSL also integrated to identify risk and vulnerability and hotspots. Now if we look at heat wave indicator of maximum heat wave temperature is the highest temperature among all the heat wave days in a year. So here you can see that this 2003 to 2019 this has been done the study, and here you can see the considerable area which is increasing in highest range of temperature. Here you can see there's some of the area which are showing more number of grids in the highest range of your heat wave temperature. So this is mostly these years were considered as more high heat wave period. Now if we look at the average heat wave duration, then also we can see like some of the areas, some of the years like grid, and the major conclusion which we have seen that 2009 to 2019 this decade has shown more number of years into heat wave, like more years are falling into this high value of indicators. Similar has been observed with your maximum heat wave duration. This is the longest duration for which heat wave continued, and we have found that before 2019 maximum grids were falling into 1 to 3 and 4 to 6 range, whereas after 2009 the range has been shifted from the upper category, like 7 to 9 category has also increased. So this heat wave indicators has been calculated, all 7 heat wave indicator has been calculated, and using weights calculated using AHPI, they has been combined together, and combined heat wave indicator layer was generated. Now here we have found that Delhi is showing the quite high heat wave indicator value, and Haryana region and some regions of Punjab and UP is also showing high values of heat wave. Now land use transformation layer was also generated, where land use was taken from 2005-6 to 2015-16, and that has been the land cover classes has been classified with respect to their impact on heat wave. Like forest to forest was considered as the feedback ranking was considered very low, whereas built up to built up or cropland to built up or forest to built up was considered as a high feedback ranking, so that given in high ranking. And similarly GHSL population with respect to population density, it has been given the ranking, and when all three of them are combined, we have found that there are like good amount of heat wave hotspot in Delhi and its surrounding region and some part of the Punjab. When this built up, the change has also been calculated with respect to your 2005, 2010 and 2016, and it has been considered based on your 2005-6 was considered as the base data, and change in heat wave indicator was studied. So we can see that 2015-16 there is a increase in your average heat wave duration, longest heat wave duration, cumulative heat wave, and total heat wave events, and built up has shown more consistent and prominent heat waves, increase in built up. So this is urban and rural area, they experience like different urban heat island. So there is less increase in heat wave intensity as compared to duration and frequency, but frequency is considered, duration and frequency has quite a good impact on your human health, mortality and morbidity. So if we summarize the whole discussion which we had carried out, deliberation, like geospatial data, they provide multiple data sets at varying scales and resolution, and it can be effectively used for your study, analysis and modeling of various aspects of urban microclimate and heat wave. Like we can study in detail urban structure, like urban permeability, urban geometry, it's a 3D configuration, urban fabric means is composition of material, urban metabolism means activity or anthropogenic heat, and urban heat island, ventilation patterns, your heat wave analysis and hotspot identification. Even remote sensing data or geospatial data provide various data sets for detailed parameterization or classification urban areas for weather models, and the detailed parameterization and classified outputs can go as an input to high resolution urban climate modeling. Even different aspect of your land surface parameters such as leaf area index or NDVI or vegetation fraction or FPAR, F cover, they also been retrieved from or obtained from your remote sensing or geospatial data. So these are the key publications, and this is thank you for your patience listening. And the questions, I'll like to take some questions.